I'm back. No, I'm not. I'm back, and I'm here to talk to you about some process statistics. First, I'd like to apologize to my long-term viewers. My mic recently died, and so the quality of my voice is going to be quite a bit worse than some of my older videos. And by recently died, I mean it died about 4 months ago, and I just haven't gone and bought a new one yet. So, what I'm looking at here today is data that's coming off of vision AOI measurements for extremely high volume products. These are like synthetic data that I've generated just to show a bunch of different things that show up in this kind of data. And the data that we're getting off of an AOI is basically a CSV file that has just a list of numbers on it. And we're just looking through all these numbers to see. So we've got one in particular that's interesting, and we want to see what the variance is of it because it's critical to the performance or function of the product. So on this product, we're going to be looking at this diameter here, and we're just going to look at what does it look like. This is normal stuff that you do in statistics. You might look at summary, which is your mean, median, your standard deviation, the number of parts that we ran, which is 100,000 in this case. You might look at the running chart, which this looks like a normal distribution, meaning there's like no discernible pattern to it. It all looks really nice. One thing that you might want to do is look at how the actual ordering of these. So I'll just connect those. And it is going up and down, but it looks relatively random. Maybe there might be some kind of cycle here where it's repeating every number of parts, but this is not that useful right now. And when we're looking at this data, this stuff normally has a bunch of cavities. So if we want to look and see, okay, maybe it has three cavities, I'm going to clear this, add in three, and we'll view that running chart again and zoom in. It looks maybe just a little bit more ordered, right? But I don't really want to have to go pointing in a bunch of different numbers to try to find out what looks perfect. So what you can do is this data is essentially normally distributed. And if you take the fast Fourier transform of a cyclical set of data, the actual like lower frequency cycles will show up regardless of the small noise of statistical processes that are just random, because those will end up as super high frequency noise. So like this jump from here to here is relatively small. It'll be very high frequency to make that happen. Whereas the general trend from, say, this clump of high values to this clump of high values is going to be a lot lower frequency and not affected as much by noise that's just generated by the statistics of the process. So what you can do is take that fast Fourier transform of the data. I'm going to clear this, set it back to 1, and do a cycle spectrum. So this will kind of tell you what the likely number of parts it takes for the cycle to repeat. In this case, it's saying 19, and that's because there's a thing called uh, bin uh, bin or phase leakage in here, where some of the data from 16 is bleeding out to the left and right. In this case, the true number is 16, and in most manufacturing processes that I deal with, the processes deal in powers of 2. So we either have 2 cavities, 4 cavities, 8 cavities, 16 cavities, and that's the same for most tooling that we deal with. We don't deal with prime numbers for like we want to have 5 parts run off of this. It's that just never really happens for us. So I know that this looks like a 16. It matches closest to 16 values that we expect. So I'm going to put in that value here for the number of cavities. And we can look at the running chart first, just to have a zoom in and see if it's more ordered or not. Just looking at it right now, you can say, yep, that looks way more ordered. That's really weird. And just of note, this data does not have the actual cavities attached to it. This is random data that I just have, we're taking measurement of part after part after part. I don't know what the actual cavity is here, but this process of setting this up where it does the fast Fourier transform tells you the number of cavities, and that lets you line it up so that you're seeing the variance of just the cavity, what the process capability is of a single cavity in here. And if we look back at that fast Fourier transform after we split it up into 16, you'll see that basically it's a flat line. There's no discernible peaks, uh, meaning that there's unlikely to be another set of cycles in this data. If there was another peak at, say, 2 or at 8, it might mean that we have a cycle on 16 times 2, which would be 32, or 16 times 8, 500, or 256. But in this case, we don't have to deal with that. We're just going to work on the next step. So this is clean data. This data doesn't have any issues with it. It's perfect. All of our parts are coming in as expected. But that's not what we get in the real world. In the real world, we have lot shifts. So in between each set of parts, we run a bunch of parts, and you'll see in this running that there's clear shifts in the data. And that's because, so when you insert molds some plastic on top of metal, that metal might be different from lot to lot because they make, say, 7,000 parts or 10,000 parts all at once, and then they'll take it down, put it back up, run it again. So that process introduces its own variation that you can see here in these distinct shifts in the process. So that's one thing that is also bad when we try to do the naive cavity cycles and we look at a box plot of these things. These look kind of spread out. If we jump back to our other example real quick, where we had no slip on the same data, we look at our box plots, the data is much more finely categorized into the cavities. That's because this is basically ignoring any shifts that you would see lot to lot. And that lot to lot variation, it's important to know where your variations are coming from. Are they coming from the process that you're dealing with right now, or are they coming from an incoming good level, which would be a lot to lot variation? But that's not the worst of it. Also, in the processes that we run, we've got something called slip, which is where if we have a bad set of parts, or we've got a bad part, we'll punch it out so that it's not going to be measured anymore. So we're maybe skipping every 15th part or every 100th part, and that throws off our cycle so that a naive assign 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 2. When you do that process, you start getting misalignments between the actual cavity data and your assumed cavity data, which introduces its own misalignment to what you would expect your cavities to be. And if we look at the box plot for this now, basically we see that the data is all perfectly uniform. You can't see any data here. And that's because we've got lot to lot shifts that are spreading things out, and then we have a shift between each of the different cavities from slip. So the peak of purple is slipping into brown, or maybe brown is slipping into purple, and essentially everything's kind of getting evened out across this data that we're looking at in this visualizer. That's not good. So what you want to do with that set of data is you want to remove the slip. And this dashboard here will do that. There's a set amount of slip in here if we assume that there's a cycle of 16, which we know from the fast Fourier transform Welch method that there's going to be some cycle. And we can try to find places where that cycle doesn't match up with the expected cycle. And this chart will do that. In this case, our data doesn't really have a whole lot of cavity variance up and down. This is just because each of these sets of data is a different set of data. But the variance between each cavity varies quite a bit. And this is removing the slip out of that system. And this is also, this chart here in the middle left is also removing the lot-to-lot variance. So this should be our true cavity capability. And if we looked at how do we get this, we would say, I'm just going to look at whatever in this set of data is the most consistent. So in here, I would say it looks like from maybe 15,000 to 30,000 parts, this is a very nice even set of data. So I'm going to take that as my reference. And we're only going to look at this data. And because we're only looking at this data, we know, and it's even, we can say this doesn't have any lot-to-lot variance. So we just remove lot-to-lot variance there. And we can look at just our cavity variance and our like shift between cavities variance. So if we go back and look at these box plots in here, this version is the naive version where you just set it by 15. I'm gonna, for demonstration purposes, go back over here and add this as if we were just looking at that nice data that was only in one block, in one lot. If we look at that data just in one lot, you see a clear set of distributions here. And this set of distributions might not be that exciting to you at first because this is just a whole bunch of distributions. What are you going to do to fix this? You're not on the kinds of parts that I deal with. This is about right where we've got a shift of 0.03 or 0.02 between a bunch of these cavities. So there's not a way that we're going to go shim these parts so that they're lined up. And these dimensions are in millimeters. So this is, a thou difference between each of these median points. But because this is staggered like this means that there's kind of two things here. When you've got a mold, you've got like two sets of parts that are made. You've got a mold, and then you've got a bunch of cavities in that mold. These cavities here can be misaligned in X and Y for each single one of them. It's not much. It's whatever manufacturing tolerance that is. It's normally 0.005 or 0.001, or rather not an extra zero there, 0.01, and these are in millimeters again. So you've got a little bit of variance that's introduced from having a pocket in a block. These are just empty pockets here into a piece of steel. And then the way cavities for molding work is we normally set a bunch of inserts in here that are all exactly the same. And our part is, again, another square block that fits into this square block. And this has a feature on it, and that feature is critical. So we've got three of these. And each one of these critical features with respect to its own edge is shifted left or right, up and down. So you might see where I'm going with this. If this piece is here and they both happen to be shifted far left and far left, then this cavity is going to be shifted far left, and we'll be measuring that in that statistics as being out in that direction. The same thing would be with this one. Maybe this one is far left, but this one actually cancels out, so it's basically right on. And then this part here on the far right is shifted to the right, and this one also will say is shifted to the left this time, the pocket is, so that this one is basically right on. But if we wanted to try to make all of these perfect, so that the variance between each of them is basically zero, what you would want to do is you want to take each one of these cavities and you want to test it in each of these separate pockets, because maybe one of these happens to also line up with this one so that when shifted left, it gets shifted to the right. And this is really only applicable when you start getting to like very large number of cavities in a mold. So when you've got 16 different cavities, the chances of having one of these line up so that it just happens to cancel out the tolerances of manufacturing starts to become extremely likely. So what you can do is you can cycle uh, back over here. We have these distributions, and we cycle the actual cavity positions into different pockets. And then we do the same set of statistics on it. And you can separate out for each cavity, what is its shift? Is the shift 0.005? Is the shift 0.05 or zero 0.1? What's the shift of the pocket in the mold? And also by shifting the insert to a different cavity, say this one over here, you can say, now we know that the insert has different contributions. So it might shift this group up versus what it was. And if you do that over a couple of different positions for each insert, you can find out what the actual true uh, like deviation is of the insert versus the pocket to a finer accuracy than what you would be able to do just by doing extremely high accuracy measurement. Because this is actually looking at the actual end good, the functional part that's coming off of the process. So if you've got 16 pockets and you've got 16 inserts, you've got 16 squared chances of having those line up, or something similar to that. You've got like an extremely large number. This would be the number of different combinations that you have. So you've got a lot of different combinations that you can test, and a lot of these will happen to cancel out, or at least that's what tends to happen when you go to larger and larger numbers of cavities, which is kind of what this is trying to get to. It's trying to find the variations of the process for finding if it's incoming goods or not, and then it's trying to find out if it's specific cavities so that we can select those cavities and shift them to a different position to compensate for manufacturing tolerances so that our statistics, instead of ending up like this where everything's kind of distributed, and if we looked at this data as one, which would be kind of what a naive look at the histogram would be. This is a very wide histogram. You can see that our standard deviation is 0.014. If we were to shift that so that there is no, so that was with no slip, this data, no slip. If we lined everything up, that'd be like if we had the 16 cavities and we were looking at each one individually and we shifted them all so that they were lined up. This isn't going to show it, but in our histogram, we'll get a bunch of standard deviations that will all be relatively similar. In this case, it's 0.07. And that's the same across all of these. And it's across 16 cavities. So these all together would build their own larger standard distribution. But you can see that if we were to shift each of these medians to be right on top of each other, we've taken our standard distribution and cut it in half. So you can get quite a large tolerance or process capability gain just by looking at the statistics and then shifting those processes like that. As an exercise for the next thing that I'll be showing, uh, I'll show, I'll make another video where uh, I've got this lined up where these get shifted. Anyways, that's what I've been working on. It's relatively interesting to me, at least. It's very useful for debugging manufacturing lines. I'll see you guys later.